All right, welcome everyone. We're going to do something a little different today, a hands-on workshop. We're going to take a clinical challenge and solve it together, step by step. And we'll be using the key calculations that honestly unlock just about any acid-base mystery you'll come across. You ready? Let's jump right in. So here's our game plan. We'll start with a clinical case, and then we've got 3 challenges lined up for you. First, we'll calculate the anion gap. Then we'll check how the body's compensating. And finally, we'll dig into how to uncover those really tricky mixed disorders. By the end of this, you're going to have a seriously powerful toolkit ready to go. Okay, so let's meet our patient. For the next few minutes, you and I are basically detectives. And like any good detective, we start with the first set of clues, the basic metabolic panel. These numbers right here, they're the foundation for everything we're about to do. All right, here's the data dump. Sodium's 140, chloride is 105, and bicarbonate is down at 15. Now, right off the bat, that low bicarb is screaming acidosis, right? But what kind? And more importantly, is that the whole story? I bet it's not. That's the problem we're here to solve. And that brings us to challenge number 1. You know, the first step in pretty much any acid-base evaluation is always to calculate the anion gap. Think of it as our secret weapon for finding out if there's some kind of hidden, unmeasured acid just lurking in the patient's blood. And here's the formula. Super simple, right? It's just sodium minus your chloride plus your bicarb. And what that number gives you, really, is a stand-in for all the anions we don't bother measuring routinely. Things like albumin, phosphate, sulfate. If this number is off, well, that's a huge clue. All right, your turn. You're the detective now. Based on those labs we just looked at, what's this patient's anion gap? Go ahead and hit pause right now, grab a calculator, and run the numbers. See what you get.
Okay, you ready? Let's plug these in together. We've got our sodium at 140, and we subtract the sum of chloride, which is 105, and bicarb, which is 15. So that's 140 minus, 120?
And the answer is 20. If you got 20, fantastic job. But remember, a number is just a number. It's just the first clue. The real question, the important question is, what does 20 actually mean? So it's all about context, right? A normal anion gap is usually somewhere between 8 and 12. Our result? 20. That's not just a little high, it's way up there. This gives us our first diagnosis, a high anion gap metabolic acidosis, or HAGMA, and this is absolutely critical. Why? Because it tells us an unmeasured acid, think ketones, lactate, something toxic, has been dumped into the blood. This narrows down our list of suspects big time. Awesome. So we've nailed down the primary problem. It's a HAGMA. But here's the thing. The body doesn't just take this lying down. It fights back. So let's move on to our second challenge and see if the patient's lungs are actually doing their job in compensating the right way. And for this, we pull out another tool from our kit, Winter's formula. It's a really neat little equation. What it does is predict what the patient's PCO2, their carbon dioxide level, should be. See, when you have a metabolic acidosis, your lungs are supposed to kick into high gear. You start breathing faster to blow off all that CO2, which is an acid, trying to get your pH back to normal. Okay, you know the drill. Challenge number 2 is on you. Using that same bicarb value of 15, what's the expected PCO2 range for this patient? Go ahead, pause right here, plug it into the formula, and see what you get. All right, let's see how you did. We take 1.5 and multiply it by our bicarb, which is 15. That gets us 22.5. Then we just add 8. So that gives us a target PCO2 of about 30.5. But don't forget, Winter's formula always has that little plus or minus 2 at the end. That's key. So what we're really looking for is a PCO2 somewhere between 28.5 and 32.5. If the patient's actual blood gas value falls in that window, perfect. The lungs are doing exactly what they should be. But if it's higher or lower, oh, that's a massive red flag. It tells you there's a second problem, a respiratory disorder, piled on top of the first one. Okay, time for our final challenge. And this one's a little more advanced. You see, sometimes you can have 2 different metabolic problems happening at the exact same time, and they can actually hide each other. So we're going to use a really cool technique called the delta-delta to sniff out these hidden disorders. The logic behind this is actually kind of beautiful. In a simple, straightforward, high anion gap acidosis, there's a perfect trade-off. For every 1 point the anion gap goes up because of that new acid, the bicarbonate should go down by 1 point to buffer it. It's a 1-to-1 relationship. If that ratio is broken, Well, that means something else is messing with the bicarbonate, either pushing it up or pulling it down even more. So to see this in action, let's look at a brand new case. This patient comes in with an anion gap of 24, so it's high, and a bicarbonate of 10, which is low. We know for sure there's a hagma going on, but the question is there something else hiding in there too? Let's walk through the steps. First up, the delta AG, which is just the change in the anion gap. The patient's is 24, and let's say a normal gap is 10, so the gap went up by 14. Got it? Okay, next, the delta HCO3, the change in bicarb. Normal is around 25, our patient's is 10, so the bicarb dropped by 15. Now for the magic part, we compare them. The gap went up by 14, and the bicarb went down by 15. Look at that, those numbers are almost identical. That near 1-to-1 ratio tells you this is a pure, simple hagma. Nothing else is going on.
And this is what makes this calculation so powerful. Just imagine, what if that bicarb was 18 instead of 10? Well, it would be way higher than we'd expect based on the anion gap, right? That suggests a metabolic alkalosis is also present, pushing the bicarb up. Or what if the bicarb was like 5? That's way lower than expected, which points to a second, non-anion gap acidosis that's dragging it down even further. See? It's how you unmask two problems at once. It's brilliant.
And just like that, you've made it through the workshop. You took on 3 big challenges, and you now know how to use 3 incredibly powerful formulas. So let's do a quick recap of the diagnostic toolkit you've just put together. It really boils down to this logical 3-step approach. Step 1, identify the main problem using the anion gap. Step 2, assess the body's response with Winter's formula. And step 3, hunt for those hidden disorders using the delta-delta. If you follow this sequence, you can confidently take on pretty much any acid-based problem that comes your way.
So I'll just leave you with this one final thought. Now that you're armed with this toolkit, what are the subtle clues, the hidden patterns that you're going to spot the next time you look at a patient's lab work? Something to think about. Thanks so much for joining me in the workshop today.